welcome to the deep dive. Today we're jumping into quantum superposition. It's really at the core of what makes quantum computing so powerful, potentially.
It really is, and we've got some great source material showing how it's moving, beyond just theory.
Yeah, exactly. So our mission today is to get a clear handle on why superposition matters and look at the actual progress being made, kind of cut through the complexity a bit.
That's good. It's a fascinating area where the fundamentals of physics meet cutting-edge tech.
Okay, let's start with the basics then. Quantum superposition. For those of us not living in the quantum realm, how does it differ from our normal, everyday experience? Like a light switch is on or off.
Right. That's the classical world. In computing, that means a bit is a 0 or it's a 1. That's it.
Simple enough.
But with quantum bits, or qubits, things get interesting. A qubit can be a 0, it can be a 1. Or, and this is superposition, it can be both 0 and 1 at the exact same time. It exists in, a combination of possibilities.
Both at once. Still messes with your head a bit. Is this where Schrodinger's cat comes in? I remember that thought experiment.
Ah, yes. Schrodinger's cat. It's maybe less a direct explanation of superposition itself and more a famous illustration of how weird quantum effects could scale up, highlighting that counterintuitive idea of multiple states coexisting until you actually look, until you measure.
Okay, so it underlines the strangeness.
Exactly. The key takeaway for computing is that this both states at once ability lets a quantum computer check, tons of possibilities simultaneously, much more efficient for certain really complex problems.
Got it. So it's not just theory anymore. You mentioned real progress. What are the highlights from the sources?
Absolutely. So one major thing from 2025, researchers managed to keep atoms in this delicate superposition state for, get this, 23 minutes.
23 minutes. Wow. That sounds long in quantum terms.
It's huge. Maintaining superposition is incredibly difficult. The slightest disturbance can collapse the state. So achieving that kind of duration is a massive step forward for stability. It shows we're getting better at controlling these quantum systems.
Which you need for actual computation.
Precisely. Longer stability means more time for calculations, more complex operations become feasible. It's crucial for building scalable quantum computers.
Okay, that makes sense. And I also saw something about topological qubits. Some big tech companies are involved.
Yes, that's another key development. Topological qubits are sort of inherently protected because of their physical structure. Their quantum information is stored in a way that's less vulnerable to local noise or interference.
So they're naturally more robust,
Yeah.
less prone to errors.
That's the hope and the promise. Error correction is a major, major hurdle in quantum computing. So building qubits that are naturally more fault tolerant, that's a really significant path forward.
So we're seeing progress on two fronts. Keeping the quantum state stable for longer and building hardware that's fundamentally more resistant to errors. How does this start translating into, real-world stuff?
Well, the potential applications are pretty transformative. Think about things like designing new materials molecule by molecule or discovering new drugs by simulating their interactions with incredible precision.
Stuff that's impossible for current computers.
Exactly. Also, breaking current encryption methods, though hopefully developing new quantum-proof ones too. And complex modeling in finance, logistics, problems with huge numbers of variables.
It really does feel like the momentum is building. And wasn't 2025 marked as, a special year for quantum?
It was, yeah. The International Year of Quantum Science and Technology.
Right.
It signals this global focus, a coordinated push from researchers, governments, industry, all aimed at harnessing these quantum phenomena, superposition included.
So putting it all together, superposition, this both states at once idea, is the engine. And now we're seeing real engineering breakthroughs in stability and hardware, making quantum computing feel much less like science fiction.
That's a great summary. The theory is meeting the practice. We're seeing tangible steps towards harnessing this fundamental quantum property.
It's been really illuminating, seeing how this abstract concept is genuinely starting to shape future technology.
It definitely makes you think, doesn't it?
Yeah.
Well, consider this. We're now actively building machines based on the principle that something can exist in multiple possibilities simultaneously. As this moves from the purely theoretical, the quantum realm, into practical tools, how might that capability challenge or even change our basic understanding of reality and potential itself? Something to ponder.